Hello, I'm Aman Sayed and this is our Data Analytics IA-2 and the topic for our IA is Predicting Lung Cancer, a Machine Learning Overview. My team members are Siddhi Somaya, Rikha Satra and Keshav Pandya. So let's go into the presentation. The main agenda of our presentation are covered in the key topics as the following. It is the introduction to lung cancer and prediction, critical factors influencing prediction, machine learning techniques, data sources and methodology, result analysis, implications for patient outcomes, and conclusion and future directions. So let's delve into the points now. Lung cancer, it is a global health challenge because of some of the following points. It has a very high mortality rate, and it is one of the leading cause of death from cancer worldwide, which emphasizes its severity. It also has a poor prognosis because it can have late stage diagnosis. For example, many people are diagnosed very well late when they have already developed lung cancer. So there is a need and an importance for early detection of if a person can have lung cancer or not. As we know, machine learning has a whole side of it, emphasizing on prediction. So machine learning can be leveraged very heavily to predict lung cancer. The critical factors in lung cancer include smoking habits, genetic predisposition, environmental factors, occupational hazards, as well as symptoms. We can leverage machine learning techniques as mentioned in a research paper, and particularly supervised learning algorithms like support vector machines, decision trees, and random forest, and we can utilize them for early detection and improving diagnostic accuracy for lung cancer. Now talking about the data set, it was obtained from data.world, as in the in our research paper the exact data set was not publicly available, so we collected a similar data set which consists of 1000 records and around 21 attributes, which are all linked and are correlated to each other and are linked to the causes of lung cancer. So for a predictive model, we first had to pre-process the data. We had to clean the data. We had to encode some of the variables and normalize it. Then we had to train our models. We use, as mentioned, 3 models we have used. We also had to get rid of some features, and then we performed analytics and evaluation whether our model is performing as intended or not. So we'll be going through the code now, and yeah, uh, for the code. Uh, First we'll import the dataset. It is the lung cancer dataset.csv, and we can explore the data and its attributes. It consists of patient ID, age, gender, air pollution, and around 24 different attributes of it. So we'll perform some pre-processing. We can drop the patient ID column because it is not relevant to our analytics. We can the level in our data indicates how likely is a person to get lung cancer. So level are low, medium, and high. We encode them with the values 0, 1, and 2. After that, we check for any missing values. Our data set did not have any missing values, so there had to be no substitutions for it. So after the pre-processing, this is roughly what the data set looks like. So after that, we proceed to split the dataset into training and testing features. We perform roughly an 80-20 split ratio for our dataset, and we use 80% for training and 20% for testing. So model implementation, as per our research paper, we are going to implement 3 models: support vector machines, decision trees, and random forest. We use the scikit-learn toolkit, which is very handful for implementing these models. So we implement the support vector machine, the decision trees, and the random forests. After implementation and calculating the respective predictions, the most important part comes in performance evaluation. We are evaluating the performance on 3 key metrics: precision tree, recall, and F1 score. So first of all, to get the output of the predicted results, we'll generate a confusion matrix. Confusion matrix basically compares the actual and the predicted values of different actual and the predicted values of our predicted of our predictions, and whether they match the values which had to be there or not. So in the SVM confusion matrix, we can see there are 8 values which are predicted to be medium risk but were actually low risk, and 3 values which are predicted to be high risk but they were actually medium risk. Same for random forest, we can see it had classified the data accurately, and for our decision tree confusion matrix, we can see 11 were predicted to be low risk when they were actually medium risk, and 24 were predicted to be medium risk when they were high risk. Now we can extract the precision recall and F1 scores using the classification report provided by scikit-learn, and we can convert it to data frames for easy plotting. And after plotting the values, class 0, class 1, class 2 represents low, medium and high cancer vulnerability levels. So we can see the precision for some of them, mainly the decision tree and support vector machines are not 100%, while for random forest we can see there are they perform well for every aspect of precision recall and F1 score. Now we can plot the accuracy scores. So we can see the support vector machines give roughly 96.3% accuracy. The decision tree gives roughly 88.33% accuracy, while the random forest gives us 100% accuracy. We can see the accuracy of our models is very high, so we have to observe whether or not they are overfitting. For overfitting, we can plot their learning curves, and we can validate the training score as well as the cross validation score for different amounts of data sets used to predict the values. So for support vector machine, we can see the following curve has been produced. For decision tree, for the following curve, and while for random forest, a straight line has been produced. Now talking about them, this SVM and the decision tree gave a reasonable deviation from the training and for the training and cross validation score, which is to be expected while learning while the model is learning for different training examples. But for the random forest, we can see that it is able to predict accurately for every level of the data set, whether 100 values have been used or 800 values have been used. We might assume them to be slightly overfitted for the data, but high capacity models like random forest can often generalize well without overfitting. The coinciding curves might just indicate that the model has found a good fit for both the training and validation sets. Based on these factors, we can generate a reasonable expectation that the models are not overfitted in this case. So coming back to the presentation, the presentation again shows us the code that we have followed, and displays the confusion matrices. Then we show the plotting values of low, medium and high level risks of cancer. When we test the accuracy of the models, then we again check for overfitting, plot the curves, and derive an output whether or not they are overfitting. So in comparison with previous studies, the research paper that we choose utilizes advanced machine learning algorithms for higher accuracy. We've also employed cross validation techniques to ensure reliability, and which is implied in the which demonstrates robustness against overfitting that we have checked. Previous studies have used fewer and less diverse data sets and lacked focused on critical predictive factors and higher susceptibility to overfitting issues. So we can now look at the real world implications of our project. Early detection benefits. Identifying lung cancer early enhances treatment options significantly. Detecting cancer as early as possible gives opportunities for medical treatments like chemotherapy and radiotherapy, which are likely to respond a lot easily and more successfully if they were detected earlier than being detected late. Reduce mortality rates. If we detect the cancer early, it can reduce the mortality rates significantly because of a timely diagnosis. Quality of life improvements. Early intervention can greatly improve patient quality of life post diagnosis, because as the cancer grows more and more and detected later on, the treatment grows to be more severe in some cases, and might intervene with a person's health and quality of life. And cost effectiveness. If a cancer is detected early, it may reduce overall healthcare costs. The challenges and limitations are again data quality issues. Some of the data might not truly be what it seems like, and it might truly be random. And the complex symptoms, complicating diagnosis and prediction efforts can be a problem. And a continuous model refinement needs to be going on, because predicted models are susceptible to false and variable data set. Therefore, to maintain accuracy, ongoing refinement and validation have to be done. Now, future directions in lung cancer prediction: integration of comprehensive data sets, which maybe contain more relevant points than the ones we've used, and may result in more accurate or more predictively accurate prediction accuracy for lung cancer. Now, advanced machine learning techniques like neural networks can be used to employ deep learning methods to enhance the predictive capabilities in lung cancer diagnostics. And some collaboration among experts might give us a really good accuracy and predictiveness for lung cancer, and might even generate some public awareness about lung cancer. In conclusion, machine learning can significantly enhance lung cancer prediction. It can uh, it can uh, it can enhance the patient's quality of life pre and post diagnosis, and ultimately it can help us save lives. So, thank you.